Have you actually thought about how the brakes works on a modern aircraft? You know, for example, what are the brakes made of? What systems govern them? How are they able to take up so much kinetic energy in case of a rejected takeoff? And what would happen if the primary hydraulic system that drives the brakes actually fails? Well, that's what we're going to be talking about today. As always, you're very welcome to Mentour, and I hope you're doing absolutely fantastic. This video is brought to you together with Brilliant. Now, it's 2021. It's a new year ahead of us, so this is time to start looking into how we can improve, and I highly recommend you to check out Brilliant. All right, the way that they are teaching is truly innovative. Obviously, they're focusing on areas like improving your fundamental math skills, or learning you how to code, or problem-solving skills, and they do so by basically chopping up a course into little pieces. All right, there are no exams, there are no grades at the end of it, and you're perfectly okay to make mistakes. Now, I've been using Brilliant together with my oldest son Lucas, and he loves the problem-solving part of it. It makes him so happy every time that he manages to solve something he didn't think he would be able to, and I think you will feel the same. So if you are interested in that, you can use the link here below. It will give you 20% off the annual fee of Brilliant. It's completely free to go and check it out. So go down, click the link, and start learning today. Okay, so brakes, guys. Now, brakes is a fascinating thing, okay? The amount of energy that the brakes of a 737 or any aircraft needs to take up in case of a rejected takeoff is astonishing. And what we will do today is I'm going to talk a bit about how the brakes are constructed. We are going to be talking about the redundancy, you know, in case something goes wrong. And also we'll be looking at things like the anti-skid system and the auto brake system towards the end. So make sure that you stay tuned. So if we start with why we need brakes in the first place, that might sound like a very silly question to ask, but the fact is that it is slightly different than why you need them on, for example, a car. So when we go out and we start moving around with the aircraft on its own power, obviously we need to be able to reduce the speed when we're taxiing, and we need to be able to stop if we have, for example, made a wrong turn when we're out taxiing or something comes up ahead of us. So that's very similar to what you do with a car. However, when you get up and you get into the takeoff position, here's where the difference starts to come. Because an aircraft has to be certified to be able to accelerate up to its takeoff speed, and then if something goes wrong at that speed, V1, which is the decision speed, we need to be able to slam onto the brakes and get the aircraft to stop within the available remaining runway distance, and that is at potentially the maximum takeoff weight of the aircraft, when the aircraft has as much kinetic energy as it will ever have. And this is more than the kinetic energy it will have during a landing. So the brakes basically needs to be built to be able to do a rejected takeoff. Okay? So what kind of energy are we talking about here? Well, if we take one of the most extreme examples there are, the Airbus A380, one of the giants of the sky. Now, it has the possibility to take off with up to 575 metric tons. And that's a lot of weight. If it is at that weight, it's going to have a V1 of approximately 170 knots. 170 knots is about 87.45 meters per second. So in order to calculate the kinetic energy it has at that point, you need to take half of the mass of the aircraft times velocity squared. So that's 0.5 times 575,000 then, times 87.45-ish squared. And that will come out as 2.2 gigajoules of energy. To put that in perspective, that's about as much as the average lightning strike. All right? It's an enormous amount of energy. And I'm betting that you've seen this, right? When they certify the aircraft to fly, they have to show that they can do this. And they do that by loading it up to maximum takeoff weight and accelerating it up to V1, slamming on the brakes, and getting it to a stop. And when they do that, I'm sure that you've seen that the brakes heat up until they're fuming, right? Until they're glowing red of energy. So the Airbus A380 obviously is an extreme example. It has 16 different brake wheel pairs with some enormous brakes in it. But the 737-800, it comes up to quite a lot of energy as well. And the way that it works is that we have brakes on both of our main wheels, right? So there's 2 sets of wheels on each side. Both of them, or all 4 of them, have brakes inside of them. And the nose wheel does not have any brakes. I don't know of any aircraft, maybe you do, that has brakes on the nose wheel. But the main wheels, that's where almost all of the weight of the aircraft is kind of set. That's where the braking takes place. So we use something called disc brakes. Okay, that's similar to what you see on your car, but in the case of an aircraft, you have several discs. So inside of each wheel, you have a couple of sets of different discs. They are stator discs, that's discs that are standing still, and then you have rotating discs. Those are rotating with the speed of the wheel. Connected to that, on the 737, you have hydraulic actuators. Now, some aircraft use electromechanic actuators as well. I think the Airbus A380 is doing that, but most aircraft use hydraulic actuators for the brakes. Those actuators are basically pistons that when we apply braking, and we do that by using our toe brakes on the top of the toes, right? That's where we have our brakes. So in order to activate the brakes, we just tilt the top forward. That will send a signal to those hydraulic pistons, and they will start pushing the stator and rotor discs together. When they do, that will, through the friction, transfer the kinetic energy of the aircraft into heat. And that's how we slow the aircraft down, right? With me so far? Good. Now, the material of these brakes. There are basically 2 different types of materials that we use on the 737. You have either steel discs or you have carbon discs. When the 737 came, most of the 737s were fitted with steel brakes, right? That's because they were much cheaper to manufacture, much cheaper to buy. The carbon brakes tended to be fitted in the beginning to high performance military jets and also to the bigger kind of long-haul aircraft. The reason that the airlines were willing to pay more for the carbon brakes on those aircraft was because they are significantly lighter. And if you're flying an aircraft for a really long time, well, then the overall weight reduction of the lighter carbon brakes would start to pay itself much quicker. But on the 737 that's doing short to medium haul, we tended to have steel brakes. So the downsides of having steel brakes to carbon brakes is that the steel brakes, weigh a lot more, right? The difference between steel and carbon brakes on the 737 is about 320 kilos. Okay, so that's quite a lot. The carbon brakes tends to have a workable life that's almost twice that of the steel brakes. And on top of that, obviously, carbon has a much higher heat resistance, all right? And it dissipates the heat much quicker. But if you have steel brakes on the 737, which most airlines do, well, then you have another issue. And that is that because the steel does not dissipate heat as quickly as the carbon does, then you have residual buildup of heat in the brakes. And the brakes are only really effective up to, I think it's about 650 degrees centigrade. If you start to get above that heat on the brakes, then the braking deteriorates, right? You don't get as much deceleration out of them. And because it doesn't dissipate the heat as quickly as carbon brakes does, it means that if you're doing short sectors, around an hour or so, then as you are taxiing out, you're building up heat. Every time that you're applying the brakes, you build up a little bit of heat in it. It doesn't dissipate. And then obviously if you have rejected takeoff, then it's off the chart when it comes to the heat. But even if you do a normal takeoff, you take the wheel up it still doesn't dissipate that quickly. So you take it out, that will cool it down as soon as the gear is out in the airstream, that will cool down quickly. But then you land, you brake, and obviously the temperature will then go up. You taxi in, that will add more brake energy to it. And then if the sectors are short enough, you'll see that over a day, it actually builds up so that on the last takeoff of the day, if you haven't looked carefully at your brake cooling schedules, which we do, then you could have the brakes already really hot when you have to do a rejected takeoff, and they might not be working as you want them to. This is why for each landing that we do, especially if you're landing on a short field where you have to use a lot of braking, we have a brake cooling schedule where you go in and you actually calculate the amount of energy that you're using, the amount of auto brake or the braking that you're using, and then you will get out how long you need to stay on the ground, how long the turnaround needs to be in order for the heat to come down. Some 737s have a brake temperature indicator that we can switch on and look at, but most doesn't. Okay, and on the ones that doesn't show the brake temperature, then you need to do this manual calculation whenever you have the slightest amount of doubt. Okay? What's happening lately, and this is good, is that the manufacturing of carbon brakes have become much cheaper. So now Boeing is making a huge push to retrofit carbon brakes onto most of the 737s or all of the 737s. The overall cost has started to come down to use them, which is a good thing environmentally because you're not carrying around 320 kilos that you don't need, and also you have just better brakes. But it's interesting to note that the way that you have to treat the brakes is slightly different. If you are using steel brakes, well then the main thing that will wear the steel brakes down is how much braking that you do, as in how strong braking that you do. If you do several small applications, it doesn't do much. However, with carbon brakes, it's the number of brake applications that determines the life of the brakes. So while you're taxiing out with 737 with steel brakes, you're controlling the speed constantly with just some small, soft applications of brakes to keep the speed exactly where you want it. In case of carbon, it's better to actually let the aircraft accelerate up to maybe slightly above the taxi speed that you want, and then make one continuous soft application down to a lower speed, not sit and tap the brakes. Now, let's talk about the anti-skid system, which is another fascinating system. So the anti-skid system on the 737 works very similar to the ABS, the anti-brake system of your car, in that it tries to keep the wheels from skidding. Because the tires, they will be most effective, as in the braking will be most effective when they exert the maximum amount of friction towards the ground. And they do that just before they start skidding. Right? As soon as the wheel starts skidding, it actually loses a lot of braking capability. So what the anti-skid system is doing is that it's monitoring how the wheels are moving. And as soon as it feels that it's skidding or that it's hydroplaning, for example, then it will release a bit of brake pressure until the wheel starts to rotate again and then reapply. And it does thousands of these cycles all the time. It's constantly monitoring this, and if you put a lot of braking on, you will feel that kind of feeling to the brakes, and that is the anti-skid system working. The anti-skid system is connected when you're working with your normal brake system to each of the individual wheels. If you would go into a degraded system operation because of a loss of a hydraulic system, then they will continue to monitor each wheel pair. Right, so it's slightly worse, but it's still there. And even if you're only down to brake accumulator, you still have anti-skid. If you would lose your anti-skid system, well, then you have an issue, all right? Because the amount of weight that you can carry is greatly reduced. And in most cases, you're not allowed to carry passengers with the anti-skid system and you're definitely not allowed to fly to anything other than dry runways. So it's a very, very limiting fault, but fortunately also a very rare fault. And now, since we're talking about different faults, we can go into the redundancy. Now, obviously, the brake system is an essential system. It is the most important way to get the aircraft to stop. We do have things like, for example, our flight spoilers that gives some aerodynamic drag, but the main thing that the flight spoilers do is actually to decrease the amount of lift on the wings to make all of the weight come down onto the brakes and make the brakes more efficient. That's the main thing that the flight and the ground spoilers does after landing or during a rejected takeoff. We also have the thrust reversers, but the thrust reversers actually does less to stop the aircraft than you might think, and I've done a separate video about them if you're interested in checking it out. So the brake system, we have to have it, right? It's essential. And because of that, it has a 3-step redundancy. So during normal operation, the hydraulic B system is the one that powers the brakes. If we would have a problem with pressure in the hydraulic B system, or we would have a leak of the hydraulic B system, well then the hydraulic A system jumps in automatically and takes up the load. And if it would be a really bad day and we would lose both hydraulic system A and B, well then we're down to the brake pressure accumulator, which is basically an accumulator that retains some of the pressure so that we have a couple of full applications of brakes available in case we need it. But this is very important. If you find yourself in a situation like that, where you've lost hydraulic system A and B and you manage to get yourself down onto the runway, make sure that you just give one continuous hard push on the brakes. Do not pump them, because for each time that you pump the brakes, you're going to lose pressure in the accumulator. And if you do it enough, you're going to lose all pressure and all of a sudden you have no brakes. And the only thing that's going to stop the aircraft then is going to be the use of reversers. So what about the auto brake system then? I promised to mention something about that. Well, the auto brake system is there basically to take a little bit of workload away from the pilots and make the braking experience a little bit more comfortable for the passengers. It's also there to help us during a rejected takeoff to make sure that we get the absolute best amount of braking as quickly as possible, because a rejected takeoff is a maneuver that needs to be done quickly in order to stop within the available runway distance. So when it comes to auto brake settings, you have 4 normal auto brake settings. That's auto brake 1, 2, 3 and max, where auto brake 1 gives a fairly soft deceleration rate, and then for each higher step you get a slightly higher deceleration rate. Now note that I'm not saying that it gives a certain amount of braking. It gives a predetermined deceleration rate, and that is based on the runway condition. So if the runway is wet or slippery with a certain auto brake setting, you're not going to get the same landing distance as you would on a dry runway. And that's why calculating your landing distance is really, really important. Auto brake max is a fairly interesting experience. All right, if you use auto brake max on a dry runway, you are going to be stopping and you're going to be basically, hanging in your seatbelt. This is why it's very rare to use that. But auto brake max is still less braking than max manual braking. The absolute max braking that you can get with the 737 is you applying max manual toe brakes. Right? Max is going to be less than that, even though it sounds weird. Now, there is another setting as well, and that is RTO that I started mentioning. It stands for rejected takeoff. If RTO is always armed for every single takeoff. Okay, we put it on as part of our pre-flight setup, and then it stays armed until the aircraft have accelerated above 90 knots. So this means that if you are doing a rejected takeoff prior to reaching 90 knots, well then you're going to have to brake yourself. If you, after the aircraft has reached 90 knots, close the thrust levers, the aircraft will understand that as a rejected takeoff and it will apply RTO braking. Now, RTO braking is more than max auto brake. Okay, and the important thing here is that it immediately jumps in. Okay, so this hopefully takes away some of the time it takes for us to actually, remember to apply brakes. The aircraft is already doing it for us to minimize the stopping distance in case we have to reject a takeoff at higher speed. But that's it, guys. So I love doing these technical videos and I hope that you like them as well. If you have questions about this or anything else, then as always, come in and ask me in the comments here below. You can join me inside of the Mentour Aviation app or in my Discord server. All right. I love hearing from you guys. But if you guys are interested in seeing things like how to do a rejected takeoff from inside of the cockpit and an evacuation, or a full setup until the aircraft is ready to taxi, or maybe engine failures, TCAS maneuvers, Cat 3 approaches, things like that. I highly recommend you to go in, get the Mentour Aviation app and get the all-in-one collection. Okay, it costs $20, but it's 2 hours of 360 instruction inside of the cockpit of the 737. You can look around, you can use your finger, you can swipe around, see everything. So that means that you can look at what the pilot flying is doing once, and then the next time you can look at what the pilot monitoring is doing. And all in all, I think it's a great learning tool. So get the free Mentour Aviation app and then consider getting either one of the collections or the all-in-one collection, which is the best value. Have an absolutely fantastic day wherever you are, and I'll see you next time. Bye-bye. Right guys, I really hope that you liked that. If you want more content like that, more aviation content, well then check this out. I hope that you have subscribed to the channel and that you've highlighted the little notification bell. See you inside of the Mentour Aviation app and have an absolutely fantastic day. Bye-bye.